was the Fukushima Daiichi nuclear power plant operated by Tokyo Electric Power Company. One of the world's worst nuclear disasters occurred here 2 years ago. The first hydrogen explosion occurred in Reactor 1. We filmed this from just 10 meters away.
It's now nearly 100 microsieverts. We've been told not to go closer because of radiation.
Radiation levels are still high. That's made it difficult to investigate the accident. Even now, numerous questions remain. Government officials and experts on diet panels ended their investigation last year. Efforts to identify the disaster's root causes have slowed since then. What caused this disastrous accident? NHK interviewed more than 400 people to create a detailed reconstruction of the events. We also drew on mountains of data to conduct simulations and confirm what happened. The first core meltdown occurred in Reactor 1. That set the stage for the crisis to expand. The emergency cooling system played a significant role in the disaster. Our investigation found that TEPCO missed cues that could have limited the scope of the crisis.
I suspected that the environment was becoming extremely tough for the reactor. I sometimes think, wasn't there more we could have done?
Consultations with experts also revealed a significant problem in the very foundations of the plant's safety protocols. Officials used fire engines to inject water into the reactors as a last defense against a meltdown. But it turns out that much of the water leaked through an unexpected route. Have they really done enough to determine what caused the accident? In communities debating whether to restart idled nuclear plants, some people express doubts.
It seems that efforts to pinpoint the causes have slowed. It would be hard to convince citizens to push ahead with pro-nuclear policies without clarifying what went wrong.
A series of meltdowns in the reactors at Fukushima Daiichi generated significant nuclear contamination.
It's been 2 years since one of the worst nuclear disasters in history, Level 7, took place at the Fukushima Daiichi. The Japanese government is crafting new safety standards that will set the criteria for restarting nuclear reactors. A prerequisite is fully verifying what happened at Fukushima Daiichi. Have officials done that? Before the accident, the government and the utility companies maintained that nuclear plants had foolproof safety measures and that workers could handle any unforeseen events. But the reality was different. A larger-than-predicted tsunami knocked out all power at the Fukushima Daiichi plant. Crisis unfolded inside the reactors all at once. The situation spiraled out of control. The first crisis was in Reactor 1. The cooling system failed, triggering a meltdown. Then a hydrogen explosion destroyed the building. Reactors 3 and 2 went into meltdown one after the next. Hydrogen explosions also rocked reactors 3 and 4. Massive amounts of radioactive materials flew into the atmosphere. This kind of a disaster must never happen again. We saw a need to thoroughly confirm what happened at the scene of the accident. NHK has already broadcast 2 segments in a series called Meltdown, which brought new information to light. Our third segment focuses on cooling the reactors, the only way a core meltdown could have been avoided. First, we look at Reactor 1. Its emergency cooling system stopped right after the tsunami. New evidence shows that operators could have picked up on trouble signs at a very early stage.
The first core meltdown occurred in Reactor 1. Workers were monitoring both Reactors 1 and 2 from the main control room. On March 11th, 2011, a magnitude 9.0 earthquake struck. Control rods were inserted into the reactor's cores. This procedure stops nuclear fission and is known as scram. But the temperature inside the reactors remained high at 300 degrees Celsius. Workers in the main control room had to quickly cool down the reactors. That was the only way to prevent the nuclear fuel inside from melting down. Rapid cooling could damage the reactors, so the operators turned the cooling system on and off at intervals. Up to this point, the cooling operation had proceeded according to plan, but things would soon take a sudden turn. A massive tsunami, more than 13 meters high, washed over the plant. The waves submerged a power panel at Reactor 1, cutting off electricity from the emergency diesel generator. Water also poured into the basement. Seawater flooded the emergency batteries. Now every source of power was lost. What happened to the reactor's cooling system? Reactor 1 is equipped with 2 isolation condensers for emergency cooling. Hot steam from the reactor cools and condenses as it passes through a tank filled with water. Once activated, the system will keep working without power. But workers had been operating the machinery at intervals. The system happened to be idle when all power was lost. From that point on, the reactor quickly headed into meltdown. When the tsunami hit, water filled the reactor to a depth of 4.4 meters above the nuclear fuel rods, or top of active fuel. The water level rapidly began to fall. In the confusion, the operators in the main control room did not realize that the isolation condensers had been turned off just before the blackout. They would normally check whether the system was working by looking at indicator lights above the lever. But when the power failed, those lights went out too. Was the emergency cooling system working or not? Operators in the main control room could not tell. 350 meters away in the quake-proof building, a false perception was spreading among officials. They mistakenly believed the condensers were up and running. Plant manager Masao Yoshida was supervising the overall crisis response. At his side was Masatoshi Fukura, a unit leader in charge of reactors 1 through 4.
Mr. Fukura, you assumed the isolation condensers were running even after the power outage.
Yes, that's what I assumed. I thought they were working.
Officials mistakenly believed for quite a while that Reactor 1 was safe. This is a fax sent from the quake-proof building to the Japanese government. In it, TEPCO officials report that the isolation condensers were operating about 5.5 hours after all power had been lost.
As we explained before, the isolation condensers are up and running at Reactor 1. The water level is reportedly within a safe range.
But at 9:50 p.m., as government officials held a news conference, Reactor 1 was already on the verge of melting down. Why did workers at the quake-proof building think the isolation condensers were operating? A senior TEPCO official agreed to talk to us for the first time. He says it never occurred to him that the isolation condensers were idle, because they can run without electricity.
The isolation condenser is, in a sense, a static, non-electronic device that requires no mechanical revolutionary motion whatsoever. So, even now, I think it is extremely effective. At the time, everybody, including me, was hoping that it was doing its job.
TEPCO officials were unable to prevent a meltdown in Reactor 1. But our investigation reveals they could have noticed early on that the emergency cooling system had stopped. At 4:41 p.m., 1 hour into the blackout, the batteries temporarily recovered. Gauges showing water levels inside the reactors came back on. The water level was 2.5 meters above top of active fuel. It had dropped nearly 2 meters in just 1 hour. The rapid drop prompted operators in the main control room to suspect the isolation condensers were not working. Operators immediately relayed their information to the emergency headquarters in the quake-proof building. In one corner, workers began calculating what would happen to the reactor if things continued at the current rate. This is known as a progression prediction. NHK has obtained a communication log from that time. It reads, 1 hour to top of active fuel. This means the emergency response team had received a shocking prediction. The reactor core would become exposed in just 1 hour. But this information later became buried amid other data and was never used. Multiple reactors were now in crisis. Plant manager Yoshida received more and more data.
Important information kept coming in. We wanted to make sure the plant manager, the commander, got every bit. Members of each team had to wait for their turn to report to him. That was the situation we were in. When multiple accidents on such a major scale occur at once, it's extremely difficult to share information with everyone concerned.
At 4:44 p.m., workers had another opportunity to notice that the isolation condensers were not working. The pig nose refers to two ducts. They allow steam generated by the isolation condensers to exit the reactor building. People began questioning if rising steam meant the isolation condensers were working. A TEPCO employee dispatched from the quake-proof building confirmed the presence of steam. Officials there continued to believe that the emergency cooling system was working.
We got reports saying steam was rising from the reactor building and that the isolation condensers were on. That's why I assumed they were running. I thought if they stopped, I would probably be informed. That's the kind of assumption that was going through my head.
Workers at the site testified that the steam they saw at the time was faint. That, in fact, was a major sign of trouble. What does steam discharged by a working isolation condenser look like? The United States is the leading producer of nuclear power. The 9 Mile Point nuclear station was built at around the same time as the Fukushima Daiichi plant. Every 4 years, its operators put the isolation condensers through a startup test. They say every worker knows what happens when the emergency cooling device is turned on.
When the emergency condensers are initiated, it takes whatever energy is in the reactor and just boils water.
These photos were taken 3 years ago during a startup test. Instead of being faint, a thick cloud of steam engulfs the whole building.
There's a ton of steam, and it sounds loud. I mean, it's a big rush. So it'll scare you. It'll knock your socks off if you're not prepared for it.
U.S. operators say faint steam emerges 2 to 3 hours after the isolation condensers are turned off. Reactor 1 was heading into meltdown. It turns out that the faint steam was a significant sign of the impending crisis. Why didn't TEPCO officials realize it? We discovered that TEPCO had not activated the isolation condensers in Reactor 1 for about 40 years. None of the operations staff had ever seen what kind of steam the condensers discharge when they're turned on.
I had never seen a working condenser. Any steam discharge was taken as an affirmation that the condensers were active. No one declared that they were idle. I guess we were unable to provide the kind of information to plant managers that would have pushed them to do something.
Operators and managers had a flawed understanding of a critical cooling system. TEPCO is responsible for the accident. To what extent have officials verified what happened? Last September, the company launched an in-house review of its response to the accident.
Faint.
The faint steam presented operators with a decisive opportunity to notice that the isolation condensers were not working. An internal TEPCO panel charged with confirming details of the accident also focused on this information. But people taking part in one meeting we filmed were divided over the significance of the faint steam.
Some witnesses said the steam looked faint and still.
Doesn't faint suggest they were working?
Everyone sees things differently, so the questions of how much steam is enough to say that the isolation condensers were active will vary from person to person.
Officials called a meeting to review the findings of the 3-month-long internal investigation. A senior member of the nuclear division concluded that TEPCO workers lacked basic technical skills.
We are running a live plant. It's a living creature. We must know what kind of creature it is in order to operate it safely. I suppose in some ways workers lacked focus or lacked the right kinds of operational skills.
TEPCO officials missed a number of critical opportunities. Then, 8 hours after all power was lost, workers had been dealing with multiple reactors at the same time. Then, the situation became critical in Reactor 1. The temperature of the nuclear fuel in Reactor 1 soared and released hydrogen that filled up the building. Workers at the scene had been focused on Reactor 2, but the first to melt down was Reactor 1. At about 4 o'clock the following morning, in the main control room, measurements showed an abnormally high level of radiation. "24 hours after the power went out. First, a failure in the cooling system caused a meltdown in Reactor 1. Then hydrogen inside exploded. The situation went downhill from there.
Multiple reactors simultaneously lost power. More aftershocks and tsunami could come. Even if operators had noticed the isolation condensers weren't working, they may not have been able to prevent a meltdown. They did not know how the critical cooling devices would function in a disaster. It was therefore impossible for them to make the right decisions or take appropriate actions. How well did the operators understand each of the huge array of technologies in use at the plant? Our investigation revealed another challenge: cooling nuclear reactors. The emergency cooling system wasn't operating, so workers resorted to pumping water from fire engines outside. Workers at the site came up with this as a last-ditch method of getting water into Reactor 1. Reactor 3 was the site of the next crisis. Its batteries survived the tsunami and its cooling system was running, but it was only a matter of time before the batteries would run out. At that time, operations staff were preparing to inject water using fire engines. But this last-ditch method had a major problem.
In the main control room for reactors 3 and 4, substitute water injection involves cooling a reactor by flushing it with water from fire engines or pumps. A nuclear reactor is surrounded by a network of pipes. If connected in the right way, they can be used to send water into the reactor. To do this, it is necessary to release steam from the reactor to reduce the pressure inside. Water can't flow in if the pressure is too high. But the workers had to inject water right away. Otherwise, any water remaining in the reactor could quickly evaporate and speed up the meltdown process. The operators needed to manipulate valves along the convoluted network of pipes to ensure that the water traveled along a single path. That would allow them to quickly fill the reactor with water and prevent a meltdown. The problem was that the workers had never practiced using fire engines to pump in water. At 9:25 a.m. on March 13th, operators began pumping water from fire engines into the nuclear reactor. Experts estimate that fire engines pumped more than 400 tons of water on that day. That should have been enough to cool the nuclear fuel. But the following day, hydrogen inside reactor 3 exploded. The water from the fire engines did not prevent a meltdown. Using fire engines to pump water was a fundamental part of the safety response. Why didn't it work? We performed a detailed analysis with help from experts on nuclear power and fluid engineering. The experts questioned whether there was a problem with the route used to inject water. They homed in on a device called a steam condenser. The steam condensers are outside the injection route. They take steam used for power generation, convert it into water, and then send the water out. Normally, there's hardly any water inside. But 2 weeks after the accident, TEPCO officials revealed that the steam condensers contained an unusually large amount of water.
The steam condensers seem full of water at reactors 2 and 3. The steam condensers seem full of water.
Could water from the fire engines have flowed into the steam condensers? NHK secretly obtained a diagram of reactor 3. We studied the complex piping system along with the experts.
Any valves?
There's a manual one. I wonder if there were any other outlets.
Probably not on the reactor side.
One of the experts had worked on designing nuclear power plants. He located a path.
It starts with the line. from the fire engine.
The single line highlighted in blue is for sending water from fire engines. A thin line branches off and connects to the steam condensers.
This is the line that leads to the steam condensers. It continues here.
But when we take a closer look,
The line comes back to a low-pressure condensate pump.
before the line reaches the steam condensers, it hits a pump that should block the water flow. From the piping that sends water from fire engines into the reactors, a branch splits off and leads to the steam condensers. The pump sits along this branch. Rotating blades inside the pump typically circulate water from the steam condensers. Under normal conditions, hydraulic pressure from below would have blocked the water from the fire engines. But the pump had stopped working when the tsunami knocked out the power supply. With the experts' help, we simulated the events leading up to the disaster. The blue pipes represent the line from the steam condensers. The red one above shows how water from the fire engines would have flowed. The red-tinted water represents water from the fire engines. Normally, the water should stop at the pump, but the red water goes through the pump and leaks into the tank that represents the steam condensers. The pump at reactor 3 was not operational. The lack of pressure from below allowed water from the fire engines to pass right through. It then flowed into the condensers, where the hydraulic pressure was lower. The operators had never imagined that the plant would completely lose power. That's why they didn't realize that the water could flow along an alternate route.
The pump's failure created a new route. That was a blind spot. No one had thought of this possibility.
The new route was a major reason for the meltdown. Siet in northern Italy is one of the world's largest experimental facilities. It can test high-pressure systems. Nuclear plant manufacturers worldwide use its laboratories. This device simulates a nuclear reactor. Our experts used it to reenact what happened when fire engines injected water at the Fukushima Daiichi plant.
I think there is a great interest about what happened in Fukushima. From a scientific point of view, there is a great interest at the international level, I think.
Engineers assembled parts to duplicate the conditions at Reactor 3. They even considered the thickness and length of the piping to the reactor, as well as differences in height. To figure out how much water had leaked, the engineers looked closely at the section where the water flow splits between the reactor and the steam condensers. We used a high-speed camera to record their experiment. The horizontal pipe represents the line from the fire engine to the reactor. The vertical one above simulates the leak to the steam condensers. When the fire engines started pumping water, the atmospheric pressure in the reactor was 3.5 compared to 1 in the condensers. The engineers recreated the pressure levels and observed the water flow.
Okay, we can start the acquisition.
Then, water begins gushing into the alternate path. The flow is clearly stronger than the flow to the reactor.
Low flow velocity here.
Right here, you have
Very high speed.
Wow.
Okay. Yeah.
The experts used the results to calculate how much water had flowed. Their calculations show that just 45% of the water from the fire engines reached reactor 3, but 55% leaked into the steam condensers.
If we need to inject water into the reactor pressure vessel, we need to avoid any leakage in the line. This is an important topic and must be duly investigated.
The finding is stunning. 55% of the water pumped from the fire engines leaked. Japanese experts did another simulation. It shows that a meltdown could have been avoided if the leak had been limited to 25% or less. If the water pumped in by the fire engines had made it to the reactor from the start of the injection process, a meltdown in reactor 3 might have been avoided.
The plant's operators never imagined they would have to rely completely on fire engines for water, and their initial attempt was during a crisis.
A leak can make a major difference. That was regrettable. A real pity.
Injecting water from fire engines into the reactor failed to prevent a meltdown. The reason was a pump connected to the steam condensers. This pump is like the ones at Fukushima Daiichi. The route that diverted the water gradually narrows. At the very end, the diameter is barely 3 centimeters. The slender pipe defeated a last-ditch attempt to stop a meltdown. TEPCO officials were aware at the time that their efforts weren't going well. TEPCO recorded 806 hours of video conferences among workers trying to contain the crisis. The footage contains a conversation from one of those meetings. The discussion was between plant manager Masao Yoshida, who was in the quake-proof building, and Vice President Sakae Muto, who was in charge of the nuclear power division.
Are you saying you've injected enough water to fill the reactor vessel?
Correct.
So what's happening then? Is there a leak somewhere?
As in reactor 1, the water level in reactor 3 isn't rising, even though we're injecting water. This means there's a high possibility of a bypass flow.
You mean there's an alternate route?
Right.
Lawmakers and government authorities commissioned their own investigations into the Fukushima nuclear accident. But none of their reports mention the fact that water from the fire engines had leaked.
2 years have passed. Even as we continue with our investigation, we have the sense that it's getting harder to get to the bottom of the disaster. As time goes by, memories of the people involved begin to fade, and the public gradually loses interest. There are constraints. High radiation levels make it impossible to conduct a thorough investigation. Still, there is much we can do. Our experiments and analysis are examples. Such simulations can't perfectly recreate the accident, but they can reveal weaknesses in safety measures and show where more attention is needed. We've touched on many issues in this program, issues no one was aware of before the accident. No nuclear plant is completely safe. The accident in Fukushima should prompt every person involved in nuclear power to work tirelessly for better safety. There must be no more Fukushimas. We'll keep digging to uncover the truth about the accident.